All right, there we go. So yeah, thank you everyone for joining. Welcome to our workshop, Generating Proofs with ZKM. Today we'll be diving into what ZKM is with regards to building the quantum network and how you can get involved. And we'll also do a demo for generating and verifying a proof with ZKM, with our ZKVM specifically. And I'm joined here also with Pavel, our DevRel lead, and also Kat, our BD and marketing lead. So if you have any DevRel or BD related questions, feel free to ask them directly to Pavel and Kat. But my name is Alice. I am education lead at ZKM. We basically saw that there can be a very steep learning curve associated with ZK. My main mission is to try to facilitate this learning process to be as seamless, as easy as possible to anyone who wants to learn. So no matter their background, their level of expertise, their experience, I'm currently helping to build out ZKM's education hub. It's ZKM's one-stop shop, one-stop hub for basically all things ZK. We're trying to bridge that gap of understanding and serve as a guiding tool to help learners navigate through this very complicated space. I'm also right now an educational programs manager at CryptoChicks. It's a nonprofit that provides blockchain education specifically for women. Previously, I was involved with Chorus, which is an influencer marketing platform in the Metis ecosystem. Prior to that, I was part of Metis's research center. And right now I'm also a student studying EE. And yeah, that's a little bit of my background. All right, before we go into the details of what ZKM is, I'm going to start a demo for generating and verifying a proof with our ZKVM. And while we're waiting for it to compile, I'll just go back to the main presentation. So depending on the machine that you have, the setup may take some time. You don't need to follow along with what I'm doing right now, but if you really would like, I linked the two repositories I'll be using, as well as the docs, the guides for proof generation and also verification processes. So after this presentation, if you want to try it out on your own, feel free to do so. I'll also paste these in the chat. So let me do that right now, actually. Actually, it's easier if you go code.zkm.io for the GitHub and then docs.zkm.io for the guides. So you can keep that for your reference if you want to try it out for yourself. I'll get back to going here. So for the proof generation part, I'm going to do a walkthrough with a recording that I made prior to this because of the time limit that we have for this workshop. So here is the recording. Let me make this a little slower. Let me adjust the playback speed really quickly. Okay, there we go. All right. So if you're doing this on your own, be sure to pull the latest version of the repo. That should be linked within the code.zkm.io. This first line here, right here, that first statement compiles Go code to MIPS. MIPS is the instruction set that ZK MIPS is based on. I'm just using a hello world program written in Go just for the purpose of this demo. For the second line here, we're going to produce an ELF binary file, and that will split the hello ELF into segments. So in terms of the parameters that you should specify, such as like the segment size over here, that should be based on your machine's hardware capabilities. So in the documentation, there's a separate section that shows the minimum requirements that you can use regarding segment size. So that after that runs, let me just fast forward a bit. Right now it's compiling. All right, so afterwards, when the split is complete, oh, just lost it. So when the split is complete, should say split done is here. Now for this next line, for this next command, we're generating a proof for each segment that we generated. In the previous command, we split the ELF into segments. Now we're going to be generating proofs for these individual segments. And from here, within each segment, you'll get the proof size, see how long it took. It'll also output proof done when it's finished. And for this last step, for the proof generation process, we're going to be aggregating all the proofs that were generated. So depending on your machine, it may take some time, ranges from half an hour to several hours. For mine, it was a 32 gig RAM machine, and I ran this locally. It was on the longer side because of that. It took a couple of hours, but all of these statements that I have here, they're all in the documentation. So if you want to try this on your own, feel free to look at the guides. And after, so right now, this is the proof aggregation process. In the end, after the aggregation is complete, you will receive a folder with 3 JSON files. So one is called common circuit data, and then we have, let me go back to the end, verifier only circuit data, and then proof with public inputs. And we'll be using these files for the proof verification part. Okay, so that's for the proof generation. Now for the proof verification, as we just said, we'll have these files in the verifier folder that you should keep for your reference. Let me see if I can screen share my terminal and do this live. So I think if I screen share my entire desktop, or I can just screen share the terminal itself. Okay, I think this may be easier. Okay. So over here, this is for the proof verification part. You can clone the repo for the verifier part called, let me just link that in the chat really quickly. I stop share. And here is the repo for the proof verification aspect. The NARC Plonky2 verifier. So let me go back to sharing the terminal. All right, okay. So you can just clone the repo for the verifier portion. And within the directory of that, you should copy those 3 JSON files that we saw that were generated in the previous step of the proof generation, specifically to a folder called the test data and then MIPS. So let me just CD into that. I already cloned it on my end, so we'll go there. And you should basically copy those files into first the test data folder, and then MIPS. So copy those 3 files into this specific directory. I already did that prior to starting this workshop. So I'm just going to go back here. And from here, I am first going to establish the path. And I recommend you just do this directly in your bash file so that you don't have to write this command every single time you open a new terminal window, but just do that very quickly. Oh no, permissions denied. I don't know why that's happening. Okay. This URL may not be correct, that's why. Used a semicolon instead of a colon. All right, okay, there we go. So all of this is within the verification guide as well. So I'll paste that in the chat really quickly. So if you want to follow along, feel free to do so. Here is the guide for the proof verification aspect. All right. And okay, just pasted that into the chat. I'll go back to the terminal here. And our first step, we can compile within this repository. There's a program called Benchmark, and it's a Go program, and that will convert our aggregated Plonky 2 proof into a Graph 16 proof. So build benchmark.go for that file. And then compile. So this is going to take some time. On my end, it's around like 10 to 15 minutes. So we'll pause this demo right now, wait for it to compile. I'll just go back to the main presentation. All right. Okay, so first, what exactly is ZKM? ZKM is building the quantum network using entangled rollups to enable universal settlement. Now, what does all of that mean? Let's first take a look into the idea of universal settlement. But before we can dive into that, we'll need to first cover what settlement is. In the traditional sense, settlement is the idea of finalizing some kind of operation where all of the obligations between any of the involved parties are satisfied. It's like settling a dispute, for example. But in our case, settlement is the process of finalizing a transaction. So where that transaction is not able to be reverted. So as an example of what finalization looks like, let's take a look at this page from the Kraken exchange that shows the crypto deposit processing times. Kraken basically sets some parameters for the number of required confirmations. All the different deposits that are in Kraken are required to basically receive a certain number of confirmations depending on that blockchain that it's on before the funds can be sent to that account. And that varies depending on the chain, results in different settlement times. So essentially, each network has a different finality. Basically, in order for you to cash out and to obtain that finality, you needed to wait this amount of time, depending on the network that you're using. There's never really a 100% full guarantee for finality, but after this amount of time, it becomes pretty unlikely and pretty hard for a transaction to be reverted. Generally speaking, the more confirmations there are, the smaller the risk of that happening. So like, for example, it takes around 10 minutes for a transaction to be posted in a block on Bitcoin. Kraken chooses to deposit funds on the Bitcoin network. I believe three or four confirmations. So the settlement time for that would be around 40 minutes. Ethereum has a different block time. I believe right now it's around 12.5 seconds for a transaction to be validated by proof of stake. Kraken requires around 70 confirmations over here. So the settlement time on average will take around 14 minutes. And it varies a lot. Some will take much longer, like Ethereum's proof of work. This one requires 20,000 confirmations, and that can take multiple days to settle. Settlement time is important. It's needed to avoid situations like, for example, double spending. And from the point of view from the exchange itself, like Kraken, they don't want to give you money before settling, before the transaction is finalized, because you may potentially be able to keep the money, the fiat that the exchange gives you, and also the crypto. So, I mean, sure, that's good for you, but that's really bad for the exchange. Another example, Ethereum Classic a few years ago, they had quite a few, I think multiple, 51% attacks. Some of the transactions got reverted and people were able to double spend. That resulted in them wanting to increase their wait time to better guarantee that the transaction can revert. So that's overall an example of how Kraken defines their finalization. So on to universal settlement. With settlement specifically, what we at ZKM are trying to achieve is this idea of universal settlement. For us, we aim to make this process of finalization unified across all blockchain ecosystems. So connecting all of these independent and incompatible chains. Basically, any sort of operation in a transaction that is executed in one blockchain. So that could really be anything from token transfer, a vote, any other type of data that's involved. And the results of that execution can be taken and can be used in any other blockchain. So you can finalize the transaction that you post on one blockchain, send it to another with a guarantee that that transaction cannot be reverted. But how exactly do we do this? We do this using entangled rollups. An entangled rollup is a way to trustlessly pass messages from one chain to another using zero-knowledge proofs. So message passing through ZKPs. And architecturally speaking, this is a diagram that's taken from our white paper from entangled rollups made by our R&D team. To establish the connection between these two independent blockchains, for example, we can actually use the interactions between their corresponding layer twos. So we have a way to communicate two different L1s through these L2s and also generate proofs for that communication. So as a result, I can pass basically any form of message across this entangled rollup network, even if it's across chains that are independent, incompatible with each other. So you can make actions like deposit, withdraw, transfer funds from one chain to another in the same rollup network. So from this diagram, we have two entangled chains over here. Transaction can be initiated on the source layer 1 or source layer 2, and that destination account can be on the L1 or L2. For this case, for this diagram, let's say the transaction starts on the source layer 1 and the destination account is on the source, on the destination layer 1. So L1 to another L1. Basically, from the source account, the transaction will be posted on the source's L1 rollup contract. It will then be sent to the source L2 rollup contract and be executed on its shadow contract. So in sending transactions to that shadow contract, the operations can then be executed on any other different chain within this entangled rollup network. After that execution is proved, it will be relayed to the destination layer 2 shadow contract right here. And the data from that execution would then be sent to its rollup contract over here. And then from there, the transaction can be sent to the destination's chain's layer 1 rollup contract. So over here on this 6th step, and some result like an asset transfer, for example, would occur on the destination L1 account over here. So that's an example of the interactions in that entangled rollup network for a transaction. Now going into the aspect of quantum entanglement. Just to note, we're not actually using quantum entanglement. This is just a loose analogy to describe what we're doing for ZKM's quantum network. But basically, the dictionary definition taken from Merriam-Webster of quantum entanglement is that the property of a set of subatomic particles whereby a quantum characteristic of that particle is directly and also immediately correlated with the equivalent characteristic of the others, regardless of the separation in space. So even if the particles are separated by a very large distance, it could be light years apart from each other, they are still connected and intrinsically connected and are able to affect one another. Some physicists call this phenomenon spooky action at a distance. But with a quantum network, the version that ZKM coined, what we can do is take the definition of quantum entanglement that we saw right here and replace particle with message, characteristic with properties, and space with blockchains. So now we have whereby a quantum characteristic of a message is directly and immediately correlated with the equivalent properties of the others, regardless of the separation in blockchains. And we can do this through message passing. So relaying a message that has specific properties to that kind of blockchain. It doesn't matter how separated or how incompatible these blockchains are. By separation, we don't mean like physical distance from actual quantum entanglement, but separation in terms of differences between like finality time, like what we've seen with Kraken, requiring a different number of confirmations for different chains. Like for example, the Ethereum proof of stake versus the proof of work example that we saw, those have different finality times. And also separations in terms of their compatibility with different languages, with their VMs. For example, Ethereum and Avalanche are EVM based, so Ethereum virtual machine, but there's some others like Solana, which has their own SVM. There's also Move based ones called MVM. So we're able to unite these separate, these incompatible, isolated blockchains using ZK proofs. Now, looking at the bigger picture with our quantum network, this is our overall vision. We're communicating to these different types of blockchains through L2s. So users can deposit assets into L2s, which can process transactions generally more efficiently. They overall have much greater scalability as well. And between these L2s, we have very generic message passing. So that's one of the benefits for this quantum network design, being generalizable. We're not just restricted to things like asset transfers, but we can also have, say, like governance votes, other types of use cases as well. And also, any type of communication can be done through these L2s. We're able to connect both EVM and also non-EVM solutions. So there's that interoperability aspect with the design by using this across different incompatible VMs. And another point I'd like to mention is that the design is also trustless. So entangled rollups, the quantum network, this doesn't depend on any external third-party validator. It has the capabilities of cross-chain bridging without having to implement the architecture of an actual bridge. And this network can also enable unified native liquidity across these incompatible chains. So any funds that a user deposits into an L1 within the quantum network can also be used across all the L2s within this network. And users can also withdraw to any other L1 within this network. And with our quantum network, we can also use it as a compatibility layer between any type of L2 that is built on top of any type of network. So that's the entangled rollup aspect. And in this way, all of these blockchains that we see, they're coexisting, cooperating, they're able to operate alongside each other. There's really no dominant player within this setup. And each individual segment right here. So, for example, over here with EVM, Ethereum, Universal L2, with Avalanche, Movement, Solana, that's an entangled rollup. But how they're all connected together, so this overall big picture over here, that's through our version of quantum entanglement, and that's the overall quantum network. So the individual segments are entangled rollups. The overall system network right here is the quantum network. And we're able to finalize transactions, achieve settlements on one blockchain, generate a ZK proof that this transaction happened, can't be reverted, and then relay that to a completely different, completely independent blockchain. And we're able to communicate that within this quantum network of entangled rollups. So that's the overall vision for what we want our quantum network to look like and also to embrace. All right, so I am going to check to see if from our demo, if finished compiling. All right, so let me go back to the terminal over here. We're going to continue the demo. So in our last step, we were able to compile the benchmark program and convert our aggregated Plonky2 proof that we completed in the previous step with the proof generation into our Grok16 proof. So now we can print the verifying key information, and we'll use that to modify the verifier's contract verification key. So let's do that by compiling the Gnark file over here. And again, this is all within the documentation. So if you want to follow along or do this on your own, after this workshop ends, feel free to do so. So we're just going to compile that and print the verifying key information. So from here, we're going to take this output and place it within the verifying key function in the Solidity verifier folder. I'll show you on my end what that looks like. So be sure to copy the output. I'm going to go to screen share another part. So within this verifier Solidity file, that's within test data, within MIPS, you should replace what was over here with the output that was generated. So I'm just going to replace it really quickly. And oh, okay. And just replace it with the output. So I'm just copying and pasting that there. And I'm gonna properly indent this as well. Okay. So that's within the verifying key function, within the verifier Solidity file, and within the MIPS folder within test data. Okay, so going back after we did that, let me go back to the main terminal. Okay, so we're over here. Okay, now we're ready to deploy a smart contract to the test network. We'll be using Sequoia in this case. Before you do this, you should install two tools. One is the Solidity compiler, and basically we'll be compiling the Solidity file to generate two other files. One is a binary file, which will run inside the EVM and will be deployed to that Ethereum test network. And the other file that will be generated from the Solidity compiler is the ABI file. And that's by using a tool called ABI Gen. That will basically generate the Go code to be entered into the EVM, specifically into the contract that we're going to deploy. So I already installed both those tools. The documentation has links to where you can install those tools. So if you want to do that on your own, be sure to install those tools first. So let me go back to the documentation over here and put in those commands. Okay. Sorry, just lost my terminal window. Okay, there he is. There it goes. So for this command, we can just compile the contract and generate the ABI. Oh, by the way, ABI stands for Application Binary Interface of that contract. And that's really needed to interact with the smart contract. So in order to deploy a contract from Go, we will also need to compile that smart contract to the EVM bytecode. And that's what will be sent to the data field within that transaction. So you'll need to install the Solidity compiler ahead of time. But from there, we can now generate the contract invocation code and compile the Go contract file. And that will include all the deploy methods that we'll need. Again, you'll need to install the other tool called ABI Gen ahead of time. It's just a really easy way. Well, that tool is a very easy way to interact with Ethereum using Go. Basically creates Go packages from the ABIs. So that's for this command over here, which I pasted from the guide. So now that we have compiled the Go contract file, we can go on to the last part of deploying the verifier contract. So we'll call this and then deploy. And we'll see an output of the contract address, which includes the verifier address and the transaction hash. And then you should record down the verifier address so that we can call the contract and then verify the proof. So then from here, let's do the last step for the verification. Okay, and this is all of the information that is outputted. The last part is the transaction hash for the proof verification. And you can view the transaction details for the hash on Etherscan. So I'm just going to paste this and then screen share. And since this is within the Sequoia test network, I'll just go through there and copy the transaction details for that hash on Etherscan, and we can view the details right over here. All right, so that concludes our demo. If you decide to do this on your own, you want to try it out by yourself, and if you run into any questions, run into any difficulties, feel free to contact us through our Discord. I'll just go back to screen sharing and also through our Telegram as well. All right, okay. So now in terms of the workshop task. This is what you'll be working on for the rest of the session, I believe. We have 2 parts for our workshop task. The first is designing a use case for ZKM. So any type of application or use case that you think could be useful to be built on ZKM, ZKVM. Gather those ideas that you have and just submit a forum post under the F3 use cases channel on our Discord. It's within the early contributor section within our Discord. So when you join our Discord, after you get your roles, you should be able to view all the sections. So it should be under the early contributor program section. And then from there, the forum channel called F3 use cases. And I also included the Discord invite link right here if you want to join right now, and also the QR code if that's easier. And okay, so I'll just go over this really quickly. If you need some inspiration for generating your own use case, I also included some resources that you can look at here. So for example, one use case that ZKM is working on is the entangled rollup, which was the focus of this presentation today. If you want a more extensive and comprehensive review of the details relating to entangled rollup, I linked the white paper right here. Another use case that ZKM is working on with Meta specifically is hybrid rollup, combining optimistic rollup architecture with ZKPs. If you want to read more details about that specific use case, I linked an article over here written by Ming, who is our chief research scientist. And in addition to that, we have our documentation, and it has a brief section about use cases. And very recently, a couple weeks ago, our DevRel lead, Pavel, who's also in this call today, he led a presentation on one use case for entangled rollup relating to privacy. So if you want to check that out, I also linked that over here. Now that's for the first part of our workshop task. The second, or the next part, is completing a small quiz. It will basically ask questions about the concepts and the terminologies that we saw today. So I added the link here, and then you can also scan the QR code. You can also, in addition to what F3 is rewarding you guys, you can also earn ZKM points on this quiz. And points are basically a part of our early contributor program to reward all of our participants for being early contributors. And they can be used to unlock ZKM specific rewards. So all you really need to do is provide us with your wallet address. And for each question on the quiz, I believe you can earn up to 20 points. And then the use case section, you can earn up to 100 ZKM points. Okay, so that's what you guys will be working on for the rest of the session. If you have any questions relating to your workshop task or anything from the demo, let us know. And yeah, other than that, if you have any questions now or need any support for these 2 tasks, just let us know. Feel free to ask, unmute, or type in the chat. And here's our contact information as well.
Thank you so much, Alice. That was really great. Appreciate it. Super thorough and great resources for folks to go forward and complete those tasks. So if you have any questions, you are welcome to ask them now. We'll stay on for a little bit longer. If not, you can move that into the Telegram chat and the other resources that they provided to connect with the team. In about 9 minutes, we have our next workshop starting, getting a price feed to your smart contract. And I really encourage everyone to stick around for that. We've extended the time to complete the task. So you have till May 7th at midnight to submit. So there's no rush. Access to support from now till then and afterwards as well. So thank you all for attending. Thank you so much, Alice and ZKM. We're really excited to have you support our team and support our community.
Yeah, thank you so much. Thank you all for joining us today on this early Saturday morning, or actually some of you guys are in Asia, so it's later in the evening, but thank you so much for joining. Yeah, if you have any questions at all, feel free to let us know. But other than that, if you need any support, join our Discord, feel free to contact us at any time. We're here to support you guys.
Great. And you guys are welcome to jump off whenever. We're going to stick around since our next workshop is starting on the same link shortly. So yeah, thank you and appreciate all your time.
Yeah, thank you. Oh, someone in the chat says, I don't have any wallet right now. What wallet should I create? You can create any type of wallet, but if you're a beginner, I would suggest using a MetaMask. I think that's the easiest. And that's for only if you want to earn some points. There's no preferred one for ZKM. This is just for you being able to receive your rewards. So there's not really any preferred one, whichever one works best for you. All right, any other questions?